Alrighty, so we're on the point of dealing with the output stage, and we need to add some driver transistors because the output impedance of the current source here is insufficient to allow us to drive the output stage properly. So I can move the output stage forward a little bit, and then we'll add in some transistors. So I'm going to put in a Darlington effectively. It's the easiest one to deal with. Moreover, it doesn't have some of the disadvantages of the complementary feedback pair that we might have chosen to use instead. LT Spice has this annoying thing that if you get it quite close to the edge, it gets a bit upset with you. Use Control B to back off a bit. It'll behave itself a bit better. So what we can do then is something like this. And we don't have to make these a power transistor, but we don't want to make them very small signal transistor either. Something in the middle ground, like a MJ350 and MJE340 would be acceptable. So these have got a maximum power dissipation of about 20 watts as compared with a couple of hundred, or 100-ish I think. But they, unlike the 3055 and the 2955, which have very low HFE or beta, as frequency increases, beta HFE is at DC. These have a HFE of probably about 300 or so. So they should give us a nice high input impedance looking in this way, a nice low output impedance looking up there, which would drive this 3055 quite happily. Same arguments down here. And we can run that once we've figured out what we're going to do with the feedback. So we'll run the feedback up here and see if that improves matters. So this was our output offset at the end of the last video before we added in the driver stage. Made it worse. Of course we have. Alrighty, so this was a problem. It hasn't solved this because there are other problems as well. Let's have a look here. Current out 192 microamps, current out here 13 microamps. Fair enough. Let's just try reducing these by a little bit and see if we can make some difference, because I'll reduce the ratios as well. See if it's this impedance was a bit big. I don't think it will be. No. Right, in that case it's almost certainly biasing problems. 72 picoamps, 68 or 500 milliamps. Yes, I think we need to do a little bit better with the biasing. The fact is, we've got 1 junction, 2 junction, 3 junction, 4 junctions, but only 2 junctions worth here. So really 5 diodes. Let's see how well 5 diodes goes. It's not my preferred solution, but we can give it a go. Presume we can fit 5 diodes in. This is when people resort to this sort of funny business. I'm not going to leave it like that, or if I did I'd redo the circuit a bit. Let's see if we can switch on the output stage properly. So we got 900 milliamps, that's on, and 1.5 amps. So there's, even though we've managed to switch everything on appropriately, there's still a big output offset, which is a bit concerning. We will have to find out why that is. I did think that would fix it actually. Right. Let's change this to something that I like a bit better, because I think that's a bit primitive. One of the problems with having a string of diodes like that is that you can't do anything with the temperature dependence. If I put a transistor here, and I bolt that transistor, I should get rid of the feedback for a minute, and I bolt that transistor to the heatsink that the power transistors are all on, I will be able to effectively monitor the temperature of the heatsink and therefore to some extent the junctions in the output stage, and I'll be able to have some thermal feedback. Now, the way that works is that I have some current in the output stage. That makes this transistor hot. The heat flows along the heatsink towards this transistor. This transistor will get warmer. As it gets warmer, the VBE you need to sustain a given IC drops somewhat. Or put another way, IC should go up a bit. IC goes up, VBE goes down a bit if you like. This current goes down because this is pinned at VBE. This current goes down, this current goes down. If this current goes down, that voltage there and that voltage there get a bit closer together. That will cause all these transistors to switch off a bit, which will cause them all to cool down slightly, over the order of a few minutes or so. The heatsink will cool down. Heatsink cooling down will cool this transistor, which will make the VBE needed to sustain a given IC increase somewhat, which will increase the current in this one, will increase the current in that one. We'll have this thermal regulation. It provides a similar effect as R12 and R13, but R12 and R13 operate on the current. The other thing it means is when we turn our amplifier on and we adjust R11 or R5, because we'll make one of them variable, to give us the correct quiescent conditions that we desire in our output stage, to give us the minimum distortion. And then we walk off, get a cup of tea, maybe put some music on, the whole amplifier's warmed up a bit. And that means that because these transistors are warmed up, the VBE they need to give us the quiescent condition we desire to give us the minimum distortion will have changed. But if this transistor is not connected to the same heatsink, its temperature will be unaffected. And we won't be able to have some thermal tracking of the quiescent conditions across the temperature range of the amplifier. And that's really what pinning Q16 on the heatsink does that R12 and R13 cannot give us. So you'd want to do that. And of course, if you've got diodes, especially the 4148 type diodes, they're in a little round package. There's no way to screw them onto anything. It's a bit messy to try and deal with it. Much better if you were to make this something like an MJE340, perfectly acceptable for the job. You can just bolt it to the heatsink along with all the others. As for resistors here, well, I know that I've got 0.7, 0.7, 0.7, 0.7, so I'm going to need 2.8 volts in total, 0.7 here. Let's make that, I don't know, 2.2k. We've got 10 milliamps or 11 milliamps down here to play with, so we need some in this pathway and some in that pathway. Exact split probably isn't very important. So we need 3 lots of 0.7, so that's going to have to be about 6.8k, I guess. We'll see how that plays out. I still don't expect it to solve this. I secretly think this is because this lot's 2 turned on. It's 2 turned on because all these 2 transistors here are jacking this voltage up a little bit too high. But we will try everything and see if it really does turn out to be what I think it is. The other thing I'd quite like to that was appalling, horrible looking bit of work. Let's have another go. That's better. Is just move these because they're not actually lined up, and that makes me sad in my heart. Let's just try and push you forward a little bit. Bloody spies. That's better. There's still some problems with this, but we'll come to those in a bit. Right, let's fire it up and see how we get on. Minus 4.2 something or other, so Yeah, alright, fine. One thing you could do, ditch this lot, couple of resistors, see how it goes, build it from there. I suspect this bit's probably alright. I think the problem is coming from here. If you're desperate to keep this stage, you can introduce a driver transistor here to give you 3 drops to the rail. That might help out, but I don't want to introduce too much complexity anyway. I'm going to get rid of this lot. If you want to put a helper in, good for you. I'm not going to stop you. Damn, that shouldn't be connected. I'm not going to put a helper in though. You put it in there anyway if you wanted to. Let's just shuffle all this off a bit. Now, in Spice, this will work perfectly well. But in the real world, damn, I missed. These 2 transistors will have slightly different beta, which is bad news. And we need to ameliorate the differences that will be caused. And Spice won't show us those unless we specifically change one of these transistors to have a different beta, which you can do. But I think it's probably beyond what we need to discuss at the moment. The way you do it is with a parameter. So let's run that and see if that improves our output offset. All it will do is allow this voltage to sit a bit close to the rail, switching this one off, which switches this one off, which allows that to float up a bit, turn these off, turn these on, and pulling that to 0. Should balance the currents out of the differential pair as well. Oh yeah, that works. Miracle, eh? 14 micrograms, 14 micrograms, 3.26. 3.26. There's a little bit flows down here, but it's not very much. 3.2611, 3.2607. 4 then. 4 microamps is the base current. Well, really. I must have added that up wrong then. 3.2611, 3.2607. 3.26. Why can't I do that in my head? That's milliamps. Ah dear, something clearly gone wrong there. Right, hang on then. If we do, just because I want to know, don't need to. Is IBQ1, IBQ14. IBQ1. Oh yeah, it's not B as it is C. Sorry, my bad. It's the collector currents we're comparing. 420 nanoamps. That's pretty small. Good difference. Leads to a low difference in the, millivolts, perfectly acceptable. Output, currents, 1.97, good God, 1.97. They're balanced, but they're very high. So operating class A, and the power, 28 watts, so quite high. What we can do to deal with that is 6.2k. That'll switch those two off a little bit. Not much apparently. 1.6, 1.6, okay. Have I got my numbers wrong here or something? That wants to be about 3 times that. Well, that's what I heard. Alright, maybe not. Keep going down. Up. 330 milliamp, 330 milliamp. Bit less. Milliamp. Getting there, slowly. Well, we could leave it at that for now. It's probably a little bit high, but we're going to fiddle with it a bit more later. So we're broadly at the point now where we might think about running some signals and see how we get on. There are still some things that aren't right though. So if we were to mock up a transient simulation, maybe we want 3 milliseconds, get rid of everything else, and we'll set this up to have 0.3 volts, and we'll do it at 1 kilohertz. So we get 3 cycles because we've got 3 milliseconds on our simulation. We look at the output voltage. Okay. Sure enough, it's sinusoidal. Output current, much more important to be honest, but for a resistive load, the current voltage you're related by Ohm's law. So yeah, it goes up to about 220 milliamps, down to about 220 milliamps. Looks pretty sinusoidal. Should be fairly happy. If you want to know about crossover distortion, there shouldn't be any at the minute because it's somewhat overbiased. Or shouldn't be any that you can see because it's somewhat overbiased. If I look at the current there into that base, this is the error signal effectively that drives the output. It's the difference between the two inputs subtracted multiplied by the gain of this stage, which drives this this driver transistor here before the VA transistor. So any troubles you can see in this current waveform, especially around the middle, you get crossover products that look really big. If I was to underbias this enormously by making it an ohm, you'd probably see that quite plainly. Yep, they're rough. It's terribly underbiased. If I looked at the current, you go, looks pretty good. Voltage, ace. But if we look here, you can see troubles when your amplifier's having to change it's a big error here, and it's having to change this voltage quite quickly to compensate for this terrible problem at the output. I can ameliorate that by maybe we'll go for 2.8k this time. Bit better. There's still some I can see there. Look, a funny little bit there. It's not right. You can see it here in the voltage and in the current. Much better, very pronounced there actually. Look at that little step. Then you can see in the output you don't see very much. It doesn't look too bad. If we look at the quiescent condition, 9 milliamps is not quite enough. 3.3k, 90 milliamps, doesn't take much. And we look now, that looks believable. If you wanted to know what your distortion was, you could ask the simulator for that to do a Fourier on your time domain. .4. I can never remember the syntax for this. 3 things I need: the number of harmonics I want, the frequency I want working at, the fundamental, and the node that I care about. And I haven't labelled the node that I care about either, which is troublesome. So to label a node, we'll press F4, we'll call it out, and that'll be my node. Now, because it's renumbered this node, it doesn't have any DC for it, so we have to run again. I might even move that in a bit so it doesn't crowd the label. Right. Oh yes, we're doing the Fourier, aren't we? So .4, I shall get it wrong, I'm sure. I think it's 1k, 1 kilohertz. V out, and it's 21 harmonics that I'm interested in. And we'll just drop this down somewhere, and maybe I'll move it up with the tran up the top there, one of the simulation commands. And I run it, and nothing happens, and we go into the Spice error log, and underneath all the business it's doing when it's trying to converge, we've got 9 harmonics, which means I made a mistake. It means that the order of the syntax is wrong. Let's go for that one. See how we get on there. Don't know why, but this just won't stick in my head. And it's had enough years to try. There we go. So we have should have the phase as well. The phase is important. Things that harmonics which are out of phase not can cancel completely, but say you had a third and a sixth and they're out of phase, that means every third one of those would end up cancelling. It's not necessarily a good thing, but the phases are important. It determines a lot of the wave shape. Overall, power density is not affected by the phase, but the shape of the wave is. So the thing we care about usually is the total harmonic distortion, 0.0012. Beautiful. A loudspeaker that you connect this amplifier to will probably have a distortion of about 1%. And as long as you keep your amplifier well below that, which this is, amplifier is not at fault. If you were looking to apportion blame in your amplifier system, your hi-fi system, as long as your amplifier doesn't have the most distortion in that system, or is an order of magnitude lower than the most distortion or whatever, it's perfectly acceptable. You don't have to expend a lot of effort and loads of transistors on making it better. So let's have a look at the emitter currents. I know I'm not clicking the emitter, but I'm clicking a transistor which is connected to the emitter. So we've got quite a lot of, we're pretty much in class A actually, because neither transistor ever actually switches off. We're quite close to the boundary of class AB, but we are both transistors on 360 degrees of a cycle, probably why our distortion so ace. Let's make that a little bit lower. Let's make it 3K. Ooh, hello. That was unexpected. Quick look here. Wow. It's oscillating quite merrily, isn't it? Wonder what's brought that on. And it's, let's have a look at that one. So that's, yeah, that's, looks like it's locked up. Different. This may help, or it may not. Probably not. Just why did that happen? That will be the question on everybody's lips. It was a guess. It was a guess based on experience. What happened when it wasn't there? We'll come back to this diagram, which is what I want to see in a minute. But we may as well look at this a bit more since it's happened. So what happened? Well, the blue transistor was switched off, and the black transistor, black one is the top one, was switched on. It's coming to the end of its period of being switched on, and suddenly this oscillation. So we've entered a region of GM, because GM is changing as IC changes. We've entered a region of GM where the transistor is unstable, and this oscillation is building, and it's probably quite a high frequency oscillation, and we could look at the frequency if we wanted to. Well, look, it's that's about 1 cycle, so it looks like it's about a microsecond, so around a megahertz or so. And this problem with the feedback systems where you've got lots of stages is the signals that get generated over here can end up feeding back over here and getting around the loop, and they'll pop up over here. Even though they weren't generated there, it was generated somewhere up here probably. This is the one I'm thinking of. That's where it started. Look at that classic oscillator startup. So we've managed to make these transistors oscillate because the resistance looking back here must be negative, or the resistance looking in there is negative because of the GM that we've got and the conditions that are around. Best thing we can do is almost certain that this business here is causing us some problems, because I changed that, and that's what set it off. All I really want from this stage here, this little bit, is to put a voltage between here and here. And if you had a really good battery and you put a signal in the top of your battery, it would appear at the bottom of the battery unmolested, because the internal resistance of your battery should be 0 or bloody close. Now, I've got these two resistors, and I've got this transistor that's passing some current. It's not a great deal, 11 milliamps. So the resistance looking down this pathway and down this pathway is not going to be 0, but I really want it to be 0, because all I want is to spread these voltages out. So if I put a capacitor there, Any high frequency signals like this annoying oscillation that's appeared should choose the capacitor rather than choosing my circuit, and even having this capacitor here should make the impedance that this circuit presents looking up into this base effectively smaller from a signals point of view, connecting this base and this base together. This capacitor has other job as well, which we will come back to, and frustratingly it's a job that I was getting onto and I need to take it away to show you the thing I want to show you, but let's run it and see how we get on. So oscillation magically gone away. If I look here, actually as it hasn't done everything I hoped it wouldn't. We go back to these two signals, which are the currents in the emitters. Let me underbias it a little bit more. Okay. Now if you look here, the turn on, imagine a straight line and a straight line, right? But the actual turn off is a much more gradual thing. If this one was the same, it would appear sort of there, like that. There's this extra bit. This extra bit of current keeps flowing, it's lingering on, not switching off properly. It's a subtle thing, and if this bloody capacitor wasn't there, it'd be much more obvious. But it's still not right. If I take the capacitor away, of course the damn thing will oscillate, but such is life. And if I was to look at the blue one, you can see it as well. There's a very clean turn on, and it's dragging his feet about switching off. So both transistors are doing it. They're dragging their feet about switching off. There. The reason is, if I zoom in a bit, when we want to switch off this transistor, we have to extract the base charge, which is there. And if we can't do that, the base charge has to recombine. Minority carriers in the base have to recombine with the majority carriers, and that takes time. And only when all the carriers have recombined is the device going to be switched off. If we don't pull that charge out, we'll have this lingering switch off. Now it doesn't really matter in this situation, but if you were making a switch mode power supply, this would be the end of the world. Maybe not quite, but it certainly wouldn't be a good thing, and you definitely want to do something about it because it would represent a loss of efficiency, because you'd end up dissipating some power somewhere that you don't want to. So we should deal with it. Problem is we're switching off this one, which switches off this one, so as we need to suck charge out of here, this pathway doesn't want to take any more current. Bugger. That's no good. We need to provide an extra way for this charge in this transistor to leave. So what we can do is put a little resistor in, just here. Hopefully I've got that in the right spot. Yeah, it looks like it. So now, charge leaving here can flow down there and end up in here, provided it can pass through the resistor, which is great, because when we switch off this one, the very next thing that's going to happen is this one switches on. Since we can take some charge from here, put it down there, no problem. Other thing we can do, of course, is there'll be a quiescent current here, because Q2 will now pass a current not only into Q12, also through R17 into Q15 into the rail. So we pick some value, it doesn't really matter, let's call it 220, or 200. 200 doesn't exist. Well, it does in E24, but in E12 it doesn't. The problem is we need to get this charge out quite quickly and get it down there quite quickly. Putting this resistor in the way is troublesome. If we don't put the resistor in the way and we turn these both on a little bit, there'll be a short through the rails and the transistors will blow up, so that's no good. We can put another little capacitor in, which is why this capacitor did some good. It allowed us to get the charge quickly between these two, and it stopped the oscillation. Or rather, it didn't allow the oscillation to begin. It removed the conditions conducive to oscillation. There we go, nailed it. Why didn't I say that first time? Put a little cap in here. The feedback is a bit of a nuisance there. We might move it. Let's move the feedback. It looks ugly. There you go. That's still horrific. Hang on, I've got an idea. There you go. Right. Doesn't have to be very big because it's going to be quite a transient thing. We should see the slow turn-offs snappy now. Ta-da! In fact, it's a bit underbiased. see that because they've got this funny little thing going on. And if I look back at the place that I love to look when I want to know about the distortion, sure enough, it's wriggling and it's horrible. Make that a bit bigger. 3.9k. That's a bit better. Quiescent current, 250 milli. That's pretty high. 3.3k. 34. That's better. That's more or less bang. About 50 milliamps is pretty good going. If we look at those turn-offs again, see how they're symmetrical? They never look any different to each other. That shows you it's going to be alright. The fact that there's quite a big crossover region where they're both on, that's okay. The point is that the shaping in this region, they're the same. Doesn't matter how biased or underbiased it is, bias it down a little bit more. See how they're all the same shape now, there's no lingering. That's important. It's not the end of the world, but it would bother me. You don't have to do it this way, of course. There's a lot of possibilities in output stage arrangement. If you don't fancy that, what you can do is have a resistor in here and a resistor in here and hook the two together. So you could do this sort of thing. You still want that cap. I'll put it back in a minute. Works perfectly well. The turn on and the turn off are now looking a little bit slower, but it might just be my eyes playing tricks with me. What's happening now is this transistor and this transistor are operating to drive the current into the output, whereas before they were just sharing a current out between themselves and driving these transistors. They're still driving these output transistors, but they are also driving the output themselves. So if I was to look at these currents, we can see there is some. That's weird, isn't it? Got to remember these are both above the axis. That's the key thing. So they're not looking at the usual things that you look at. The fact they're in antiphase is just because the transistors are going antiphase. But these are both class A. They're never switched off. That's one. See, it goes down to 2 megahertz, but it doesn't hit the rail. And the same one here. There you go. So they're both in class A. They're ugly as can be, but that's the way of things. Why might that be? You'd want to investigate probably the size of this resistor a bit, and also the current demands of that transistor and that transistor will have something to do with it. Might be worth making these a bit smaller. Try and up the driver current, because a 5 milliamps is not much in the way of driver current. Maybe a bit more still. Don't want to go too crazy because it ups your power dissipation unnecessarily. But so when you change your output stage, you would change the amount of biasing you need. Still a little bit. I can still. Sure, I thought I saw something there's a little notch just there, isn't there? When I zoom in, it goes away. Maybe not. So we should see maybe nicer. No, that's better. So we don't have any, not any, but we don't have much in the way of distortion there in the base currents. Although they're far from even. We look in the collector currents. They are very similar. If you want to see them, not similar in magnitude, but similar in overall shape. It's believable. Current, the distortion now is probably very low again. Gone up a bit, but we're in class AB before we're in class A. if you want to know about the relative merits and demerits of the various choices of output stage, Self has rather a long discussion of them. My preference is for the first one. If you pin this node in the middle, it means that this node can never fall below this node without this stage switching off, because the current would be the wrong way in this resistor. Whereas in the other one, where we've just got the 220, you can allow the voltage between these across these two to flap however you need it to switch these power transistors off and on as appropriate. So being able to move this voltage with more freedom might give you an advantage when it comes to switching. It might make it slightly more unstable as well. At the very least, it saves you one resistor. So that's my excuse for doing it that way. I don't have to pay for the extra resistor. You can do either way, it's not wrong. Back to the original method, and the biasing is now a little bit high. Righty, so I'll change the biasing. That's a bit better. If I want to see it again, I can just move it like that. So it's when you're looking at output stage type things, you really want to be looking at the currents in each half of the circuit, not getting too obsessed with the output voltage. It doesn't really tell you very much. When you look at distortion, really it's the current into the VO stage, or the voltage on the VO stage base, that tells you what you need to know. Right, so we must discuss now at some point the compensation of the amplifier, and then we're probably more or less there.